recall that 2130 is a course on multivariable calculus. Chapter 12 starts that process. Chapter 11 gave us a number of tools that will be indispensable in our discussions. If you think about real-world situations, and you think about one thing depending upon something, it is probably unrealistic to think that most things depend upon only one other thing. Most things depend upon a multitude of things. For instance, if we wanted to talk about the temperature represented by T, when you're watching this video, the room in which you're watching it, then the temperature at various points in that room is liable to vary. So if we had an X, Y, Z coordinate system, then that temperature would depend upon X and Y and Z. But would also depend upon when you take it, because the temperature is not likely to be constant as time progresses. So what you would have then is that big T depends upon X, Y, Z, and little t for time, and we call that a function of 4 variables. Something more involved yet, visualize that I am a pitcher, and I'm going to throw the ball to home plate. And I want to describe the ball during its flight. What kind of things would I describe? Well, one, I would describe where it is at any given time, right? So that describes its position. But I'm also interested in the fact is, what direction is it going in? So that would mean talking about its velocity. So I would have an X component of velocity, a Y component of velocity, and a Z component of velocity. I also have a wicked curveball, which means I'm going to start spinning the ball, not just throwing it flat like a knuckleball. And so you might have, let's say, components, be some more, say, omega 1 and omega 2 and omega 3, representing then rotational aspects of this ball. So what do we got here then? To describe the ball, we have a function of 3, 6, 9, 10 variables, and that's a physically realistic situation. So multivariable functions are important to us. A variable z is said to be a function of variables x and y if for each pair of values of x and y, there is a unique value of z. So we're talking now simply about a function of 2 variables, and we would write therefore that z is equal to some function of x and y. The set of values that x and y can take on is called the domain of the function, and you can visualize that as some kind of an area in the xy plane. So you have some area down here, we call it D, say I am only allowed to take values of x and y that correspond to points in this region, so that would be the domain of the function. We can visualize the function if you said, let's visualize function by drawing the surface with the equation z is equal to f of x and y. And this is why we were practicing drawing surfaces way back at the beginning of the course, in preparation for now visualizing functions. So what you do then is you draw that surface, but you only draw that part of the surface that projects down onto the xy plane. So you're given a point here, x and y, and that height to that surface, that's the value of the function at that point x and y. So you visualize values of the function as the height of the surface above the domain in the xy plane. This is very nice for functions and variables. But if you had a function of 3 variables, x and y and z, I got a little bit of a problem visually. I would have to put this say equal to u, and then I would say the domain of the function is some volume in space, and then I have to draw a u-axis perpendicular to the x and the y and the z-axis, just like we drew a z-axis here, perpendicular to the x and y axis. I would have to draw a u-axis perpendicular to the x and y and z axis. I'm in 4 space, and I have a little difficulty visualizing 4 space. So I lose the geometry. So what we're going to find as we progress through the course, this part of the course, I often use functions of 2 variables to illustrate ideas and introduce them, because I can see what's going on there. When I come to a function of more than 2 variables, I use that visualization, but I have to talk algebraically with more variables. Let's take an example, a nice simple example. Right? Example. Suppose f of x and y is equal to 2x squared plus 3y squared. Not a particularly difficult example. So we would set z is equal to 2x squared plus 3y squared. And I would say, how do you visualize that surface? And we did that back in the previous chapter. What is that? Well, you should recognize that by now. That's a bowl that opens upwards. Like that. And what are cross sections? Cross sections parallel to the xy plane, by putting z equal constant, are simply ellipses. So we would have called that non-mathematically an elliptic bowl. Right? Mathematically, it was one of our quadratures, which would have been called an elliptic paraboloid, because cross-sections this way are ellipses, and cross-sections this way vertically are parabolas. So that's what we call that. Here's one that's quite physical, and of the kind that you will see in Math 3, but much more involved, much more difficult. Suppose that I have a string of length 1 meter stretched between 0 and x equal 1 along the x-axis. I pull it tight. Then what I do is I somehow manage to get this into the shape at time t equal to 0 of the shape sine pi x. Just trying to keep things nice by putting this pi in here. You might have preferred an x in here, but then this would be a pi instead, right? So what does that look like? It looks like this. Sine curve looks like that, right? Goes up here to 1, whatever the units are, maybe 1 centimeter, right? So it's pulled tight. And then I fix this end. This end is not allowed to move, and that end is not allowed to move, and I let it go. And it's going to vibrate up and down, right? The question is, what's it going to look like as time progresses? Right? And I think you could kind of guess that in a short time it might look like this, then it might look like this, and then eventually it hit here, and it probably goes down there, right? And that is indeed true, right? For t greater than 0, y becomes a function of x and t. So y is the displacement here, right? It depends upon two things. It depends upon what the x is and what the time is. And it turns out that it's equal to the sine of pi x, the cosine of, I believe, 4 pi t. This is a description of where the mass, or where every point in the string is as time progresses. And you probably would like to maybe draw that. Right? Now this is particularly simple when I did this, and here's a displacement. If I said, no, I would like it to look like this, all right? Just grab the middle, lift it up a little bit, and then let it go. It becomes much more complicated here. This actually becomes an infinite series with sines and cosines in it, and that you're going to see in math 3. Right now we want to keep it simple. So the question is, what does that surface look like? Well, it does look like the following. So let me try and describe it. So we'll put an x-axis here, we'll put a t-axis there, and a y-axis. So at time t equal to 0, we have this. It looks like that. Right? That's at time t equal to 0. Right? If you progress outwards a little bit, and then draw it again, that point is fixed, that point is fixed. It's got the same shape, but it is not as high. And then eventually over here, in fact, right, at t equal to, what happens at t equal to a quarter? If you put in t is equal to a quarter, no, I want an eighth. Let's do an eighth. T is equal to 1/8. If you put in t equal to 1/8, then you're finding out what is the position of a string after 1/8 of a second. So if I put in t equals 1/8 over here, this becomes a 4 pi 1 over 8, which is a cosine of pi over 2. But the cosine of pi over 2 is 0, which means at that time, this string is going to be completely horizontal. What happens if you put it? So that's what it looks like. When t is equal to 1 over 8, then y of x and 1 over 8 is equal to 0. What if you put in t is equal to a quarter of x, right? Then what have you got? Y of x and 1/4 is equal to put a quarter in here, then the 4 is going to get cosine of pi, that's minus sine pi x. So now, after another eighth of a second, the string is now underneath the xt plane, exactly this thing turned upside down. Can you kind of visualize then what the surface is going to look like? Right? It's up here, and then it kind of gets smaller, hits the xy plane, then it goes down underneath, then it comes up. It's like a wave. Agreed? Looking like a wave. If you cross-sect with plane, say t is equal to t0. So you take a t0 here, and you draw the cross-section, you take the surface, and you slice down through it. What is that? What is it going to do? Is that not going to be cross-section plane? Gives position of string at this time. You could also take cross-sections with plane x equal x0. So now you slice with the plane this way. What are you going to see? You're not going to see a curve that goes like this. What's that? That's a history of the displacement of that point in the string. It's going to go like that, and that's its displacement. It gives a history of displacements of this point in the string. So you can see that the cross sections here are very meaningful They weren't with my z equal 2x squared plus 3y squared because I had no idea what z represented physically. Here, I know what y represents physically, and I know therefore what these cross sections represent physically. There is another way that you all have seen to represent a surface. And I'm going to describe it to you, and then I'm going to ask you, where have you seen it? So back to my first example. Z is equal to 2x squared plus 3y squared. So let's redraw that one. And remember, it was our elliptic bowl. It went like this. Suppose I intersect, take a cross section with plane Z is equal to K. If I do that, then I get K is equal to 2x squared plus 3y squared, along with Z is equal to K, is that equation of that cross section. I'm slicing the surface horizontally, and I'm getting therefore something that looks like that. Agreed it? An ellipse. Let me draw that ellipse in the xy plane. There it is. There's that ellipse coming from some value of k. Suppose I choose a smaller k and I do the same thing. I get an ellipse that is smaller. It would be inside this one. And I could take a whole bunch of them. I take a whole bunch of cross sections and slice, and really what I'm doing is projecting these curves down into the xy plane, but I'm drawing them separately here. You'd have a bunch of these ellipses. This would be, say, for, say, k equal to, say, maybe 2, and this one is k equal to 1, this one is k equal to a half, and so on, and so on. You get these. So what you're saying is that every point on this curve, that the value of that function is 2. For every point on this curve, which is a projection of that curve there, the value of the function is 1. So these are cross sections that talk about constant values of the function. Where have you seen these before? Where have you seen drawings that look like that before? And I think you'll quickly realize that you see those on topographical maps. They don't draw surfaces like this. They draw these things. They see, this is going to mean, right? That means that this is k equal to, say, 2 kilometers and 1 kilometer and a half kilometer. Then there's a big valley here, and this surface is rising from there. You also see them on marine charts, where they represent depths rather than heights. You've seen them on climatic maps, where you have things called isothermals, that everybody on this curve, right, has the same temperature. Everybody on this curve has the same temperature. You also see isobars, right, which are points that have the same atmospheric pressure. So those things are common when you don't want to draw surfaces. In the textbook, you'll see that I used the computer to draw some surfaces, and they do an excellent job as long as you want to find out or see one function. The problem becomes when it gets to the latter part of this course, when we want to say, here's 3 or 4 surfaces, they surround some volume, and I want you to find me that volume. If you were to ask the computer to draw all 4 of them on the same page, you would not see what is going on at all. You will be able to do a far better job than the computer does. But if you got one solitary surface, you want to know what it looks like, the computers can do a good job. But we're not gonna be using them. So that's it for section 12.1.